Check. Okay, nice. So this is a new thing I'm starting where I'll be covering the parts of Weinberg. So I'm going to start with chapter 2. Chapter 1 was mostly historical facts and the story of QFT. So I'm going to start with chapter 2, in particular section 2.2, I think, and section 2.3. No, I think only section 2.2 and 2.1 as well. So it starts with a very brief review of quantum mechanics, where it says that so its notation is like this. So there is a state. So first of all, there is a Hilbert space. There is a Hilbert space H, in which states live. So in Dirac notation, the states are represented like this, and their product like this. In Weinberg, this notation is given in this form, but it's the same thing, doesn't matter. So let's say there is some vector or a state psi in this Hilbert space. So the first axiom of quantum mechanics is that all the physical states are represented by some vector in the Hilbert space. In particular, they say that it's a ray. Ray means if this state psi is multiplied by any complex number e to the power I theta, then the physical content of the state does not change. For instance, if you take the norm or you do something else with it, this phase vector is arbitrary. So all the vectors which are of this form, which would constitute a circle's worth of unit vectors, not unit vectors, a circle's worth of vectors connected to psi via rotations, all these combined, this set constitutes a ray, which is represented by this R. So this vector itself has a ray associated with it. You can imagine it in many different ways. You can think of a circle here or whatever. There are many ways to do it, or a literal ray, whatever. Yeah, so some other vector, for instance this one phi, would have its own ray associated with it, like this. For instance, this is R psi, so this I can call this whole ray. So the ray is a set of these vectors, a continuous set. So this is my R phi, for example. Okay, so again, the first axiom was about physical states or physical systems are in one-to-one association with these rays. This R is a bit funny. Okay. The second is that there exists a dot product in this space such that the dot product phi psi and psi phi are complex conjugates of each other, and these are linear. So the dot product also satisfy all those linear conditions, such as phi dotted with a psi 1 plus b psi 2 is phi psi 1 plus phi psi 2. And if there is some other let's say phi 2 plus phi 1, and there is some other let's call it b and a, capital B and capital A, then when you take a from this guy out, it would give you a star, and this is phi 1, and then similarly other terms, a star, b, phi 1, and then similarly other two terms. And it is positive definite. Psi, the norm is positive definite, and it is equal to 0 only when psi itself is 0. And other than that, we can talk about the second axiom of quantum mechanics, which is about observables, which are represented by operators. And these are Hermitian operators. Since these are Hermitian, that would guarantee that the eigenvalues are real and the eigenvectors are orthogonal. And we can say if an observable A acts on psi, it gives off its eigenvalue A, and the vector psi itself, where psi belongs to the ray that we were talking about. And the probability of, let's say you are in some ray R. So I'll draw rays like a line like this. So it's also a vector, it's also a set of vectors, whatever. So array R and some other array, let's say Rn. So if your vector lies in this ray, then the probability that you will find it in this ray would be given by the square of this modulus psi n psi, not the modulus of this dot product. This is the probability of finding a vector or finding a state in the ray R, and given that it was in the ray R. And obviously the sum of all these such probabilities would be 1, and these are roughly all the axioms of quantum mechanics. So these are all axioms. Next they talked about symmetries, and this is how I look at it. For instance, you have your physical system. It can be anything. For instance, you have your let's say you have some harmonic oscillator, and it's a quantum harmonic oscillator. You can imagine some fuzzy thing oscillating like this, and you have some coordinate system associated with it. And let's say you are measuring its center of mass or momentum or energy or anything, any observable. Let's say you are measuring the center of mass of this system is at some location R, and then you do some transformation, and or maybe you do some translation of the coordinate system such that now you are in a new coordinate system here. So now the new center of mass would be at this location. So any transformation is seen as a change in the outlook, or a change in our point of view, but that does not change the results of the possible experiments. So such a thing is called symmetry. So it says the symmetry transformations is a change in point of view that does not change the possible outcomes. So if some observer O sees a system or sees a state in some ray R, then another observer in O prime, which looks at the same system in a different ray R prime, but they okay, let me just lay out some names. So this observer R was looking at this system, and the corresponding Hilbert space H, the corresponding state was, let's say, some psi, and it corresponded to some ray R. And then this system from this observer O prime is some R prime, some state psi prime. Then the probability, and then let's say you observed it in some other state Rn, for instance, just like you did here, like some the probability that it was present in ray R, and then we observed we were asking about the probability that we will find it in some other ray Rn. So right here, let's say some Rn, and here as well another ray Rn prime. All of this is to say that even though from these two perspectives, the probability of observing the system in ray Rn, let's say, is this, and the probability of observing the system from the new point of view in some ray Rn prime, given that it was in the ray R prime, is this. The point is these two probabilities would be the same because the system is the same. So these probabilities are not dependent on who is looking at it and from where. So that's the main idea. And by the way, these symmetry transformations, for instance, here I translated my origin to some new location. I could have rotated the system to some new coordinates, or I may have boosted it towards some new axes. as all these symmetry transformations correspond to in the Hilbert space. So this much should be clear, that for instance in my original coordinate system, the system was the state was psi, and in the new one in O prime, which is might be rotated, might be translated, might be some boost or something else, the state would look different. In let's say it's psi prime, it would look different, although it's the same state, or not even the same state, but some observables that are associated to it would turn out to be the same, but the state looks different. So the state has transformed. So, and that is represented by some transformation on the Hilbert space. That is to say, some transformation, let's say A, which maps H to H itself. So some map A is there, and the theorem by Wigner shows that this map has to be unitary. That is to say, this matrix which is transforming psi to psi prime would be a unitary matrix, or it can also be anti-unitary, but we'll only talk about unitary matrices, which is U dagger should be U inverse, and linearity means that it acts on A psi plus B phi would be A U psi plus B, and so on. If it's anti-linear, that would mean that we will pull out an A star instead, I think, if I'm not wrong. But we don't really care much about this one for now, so this one suffices. Plus B phi. Yeah, okay. Next thing would be to talk about so I haven't proved this fact. This much we can see that a change in the point of view from O to O prime in the physical system would correspond to a transformation of the state in the Hilbert space, and that transformation is unitary. That I have not proved yet, but we will take that as we'll take that on face value for now. Okay, so now let's talk about let's say, and by the way, for all these things we can have some specific symmetry transformation in our minds. For instance, even though it works for non-abelian transformations as well, but we can think about a very simple case such as a translation of the origin of your coordinate system in 2D space. It's a very simple transformation. Let's say transformation number 1 could be moving like this in a 45 degrees angle. Transformation 2 could be this one, and transformation which is a combination of both of these could be this one, 3. So 3 is just 2 followed by 1, right? You can write it like this. So it's written like this because a state first 1 will act on it, then 2 will act, and that's equivalent to 3. But yeah, so but in general these things work. The point is that we can write some transformation T1, right, which could be some sort of transformation like this one, like a space-time translation in 45 degrees direction. This there can be a transformation T2, and the point is the transformation T3 also belongs to the same group. So I'm just defining that these transformations form a group, which would be that there exists the composite transformation is also part of the group. Secondly, inverses exist. For instance, you can go back to origin after T1 by applying some T1 inverse, and also identity exists. For instance, unitary operation, not unitary, identity operation, which corresponds to not doing anything here, that also exists. So due to all these things, we have a group, and these are really defined on the rays. That means the T1 takes your ray from, let's say, R to R prime, or let's say R1 to R1 prime. T2, let's say, takes R prime to, okay, let me just remove the ones from here. T2 takes R prime to R double prime, and this guy t2 t1 t2 is also a transformation. We can call it t3 if you want. This one takes r to r double prime. So these are rays, okay. And the unitary transformations that correspond to these transformation, as I said, these are abstract group elements. In Hilbert space, they would correspond to some some matrix, some unitary matrix, linear unitary matrix that acts on the state vectors. So we can have a state vector psi which belongs to this ray r, and then we can do a transformation t1 that will take it to some other vector which belongs to the ray r prime, which is some this vector, let's call it psi prime, and then followed by another one t2, which again takes this vector to some point in this ray r double prime, and let's call it psi double prime or whatever. And then of course there is also a direct transformation in the group which we are calling t3 or t2 t1 that would take us directly from this ray r to this ray r prime. But there is one possibility that this vector that corresponds to the transformation which corresponds to a unitary matrix that takes this psi vector to some other vector. It's a possible that that vector is also in this r double prime, but it's not the same as this one, as in there is some difference in the angle between these two. Some phi is there, and that means if there is some vector psi acting upon it by let's say some unitary transformation corresponding to t1 followed by another unitary transformation corresponding to t2, would give us a new transformation which corresponds to t2 t1, this transformation, the unitary matrix which corresponds to this transformation on psi. But there might be a factor of some e to the power I phi, which again can be a function of t2 and t1. We can call it phi t1 t2 or whatever you want. And also this can be on some nth vector of the let's say spectrum or anything. There can be a label here, and then that label would also be here on the angle, because this different states can correspond to different phi's. All right, so this is a possibility, and it can be shown that this psi n can be dropped off. The proof goes like this. Let's say you construct this psi n from two states. Let's call them psi a and psi b. And if you act psi t2 t1 on psi a plus psi b, for the moment I'm dropping the kets for now. And so that would be again this one acting on this one. That is equivalent to saying e to the power I phi a psi a, sorry, u t2 t1 acting on psi a. I'm just using this definition for each of the states, plus e to the power I phi b u t2 t1 acting on psi b. And on the other hand, the composite thing is just e to the power I phi a b. Wait, u t2 t1 acting on psi a plus psi b. Wait. Phi a b. This is just your yeah. So here we have psi a and plus psi b. Then we can multiply on both sides by the inverse of this u t2 t1, and we will just have this. Now since psi and psi b can be chosen arbitrarily, wait a second, we have this guy and then this guy. Yeah, so since psi and psi b can be chosen independently, so this equality can only hold if these factors are actually equal. That is to say, e to the power I phi a b and e to the power phi a and e to the power I phi b all are the same. Let's say all are e to the power I phi for some phi. So what we are saying is that these angles, that difference in the angles when we do the two transformations step by step versus we do the composite transformation, then this difference in this angle in the three cases, whether we do it on the combined psi a plus psi b or we do it separately on psi a and psi b, all these are just the same. This is what we are saying. Okay, so accordingly, what would that mean is that in the original condition, this will make this statement psi independent. That is to say, we will have u, which is a unitary operation on the Hilbert space corresponding to the transformation T2 is just e to the power I phi of some, which is a function of the transformations, and the composite transformation T2 to T1. This is the punchline. Once again, this might sound abstract, but keep in mind some trivial transformation like the one I showed before, where one could be a translation of a space-time origin by a 45 degrees in the plus right direction. Second could be the same 45 degrees thing but in the opposite direction, and the three would, or the composite of 1 and 2 would correspond to a 90 degree thing, translation in the y direction. So this is just saying that if you take the operator that takes states psi to some new states under this operation 1, and then you do another transformation on it which corresponds to a 45 degrees thing in the opposite direction, followed by another transformation. So you reach here, that is equivalent of this composite transformation. That is to say, a transformation that corresponds to a straight up shooting the coordinate origin, such as this one, and times some phase factor which might be a function of the two transformations. It is just the same thing. Okay, now this looks like the law that we have in representation theory, that a set of matrices furnish a representation of the group when d of g1 and d of g2 is just some d of g1 g2, something like that. But here we have this exponential factor here, so this is indeed a special case of this one. This one where phi is not 0, this is then called a projective representation, and in case phi is 0, then we get back our special case where we furnish a representation of the group itself, or the Lie group. Okay, there are some discussions on whether we can tell whether a state, so let me just read that out. It says that the structure of the Lie group cannot by itself tell us whether the physical state vectors furnish an ordinary or a projective representation, but as we shall see, it can tell us whether the group has an intrinsically projective representation at all. Okay, so by the way, this argument can break if you cannot write down psi n as a sum of psi a and psi b. If that happens, then you cannot say that this thing is state independent, and then in that case these transformations would be dependent on what states you are choosing. And it is possible in a case, for instance, it is believed widely that it is believed widely that it is impossible to prepare a system in a superposition of two states whose total angular momenta are integers and half integers respectively. So in such a state, the things will depend on what states we are adding up. And in such cases, we say that there are these super selection rules between different classes of states, and the phase phi may depend on which of these classes of states the operators u t2, u t1, and u t2 t1 act upon. So we can talk about this later, as does the book, and for now we'll move our attention to the Lie groups. Okay, so we have this guy in our mind. Once again, to recap, we have a Hilbert space, so always have two pictures in our mind. We have this physical system, it's doing its own thing. It might be a two body system, one body system, n body system, whatever. It might be a harmonic oscillator, might be a particle in a box, or anything. It's a physical system, and corresponding to that physical system there is a Hilbert space. And if corresponding to every state here, there is a ray, in technically a ray r, but there is one state psi and its equivalent states in the whole ray r, which are just some e to the power I theta factor times psi. And apart from the axioms of quantum mechanics, for every symmetry transformation that can be done on this system, from going to some coordinate O to O prime or some other sort of symmetry transformation, this sort of a shift in perspective on the physical picture corresponds to moving the state psi to some new state psi prime via a unitary transformation, a linear unitary transformation, although an anti-linear is also possible, it's also allowed, but we'll just look at unitary ones. And yeah, okay, yeah, so this transformation T corresponds on this side to a unitary transformation U, which is a function of T, and of course the U transformation of some one transformation followed by another transformation T2 is same as transformation corresponding to T2 T1 T2, and then if it's projective, then there is some phase vector here. And for now, let's talk about Lie groups, where we set this phase vector to 0. So we have this rule at our hands, and in particular we can say, for instance, these transformations T are labeled or are parameterized by many parameters, theta 1, theta 2, and so on. Collectively we can call them theta A, and this transformation, these might be Euler angles, these might be the boosts in a Lorentz transformation, these might be the coordinates of the space-time translation vector, or can be anything. These are continuous and real parameters. These are real parameters, and they decide what sort of transformation we are doing. Let's take a specific case. For instance, let's say you have three Euler angles, theta 1, theta 2, theta 3, and in the space of these angles, every point corresponds to some number, let's say 45 degrees, 30 degrees, and 60 degrees. That corresponds to some rotation in the physical system, physical coordinate system, by, let's say, 45 degrees in x-axis, 60 degrees in y, and something like that. The point or the origin, the 0, 0, 0, would correspond in the physical side to doing nothing, just the identity operation. And so every point here in this space of parameters is connected with identity, because remember, origin is the identity, and this is some transformation T. These two are connected to one another in a continuous fashion. Okay, and of course some other transformation which is also connected to identity might be represented by T bar or theta bar. Just bar is some way of distinguishing theta from, these thetas from these ones. We can call it theta prime or whatever. So let's call it theta bar. Obviously this A index runs over all these different thetas. So it's a vector in, so one point is a vector in this RA space. Okay, anyway, so now this condition in this new notation might be written as follows. So we do some transformation T, which depends on this set of thetas. I should write theta A, but I'll just write theta, and followed by another transformation T, which is parameterized by theta bars. Again, this is a set of A numbers, and this would be a transformation. The combined transformation would be some function of thetas and theta bars. I mean, what I mean to say is the combined transformation will have its own set of thetas. For instance, here we have some A numbers written, right? Theta 1, theta 2, and so on. Here also we have A numbers written, theta bar 1, theta bar 2, and so on. And here we will also have A numbers. And these A numbers, all of these would be some functions of theta bars and thetas. So in particular, this F is also carrying an index A. There are also F. So it's like this F1, F2, and so on. And all of these Fs are just functions of thetas and theta bars from here. So that's a pretty, like, it's a little, it might be a little confusing, but if you think about it, it will get clear. Okay, now one can imagine that if we set theta bar to be 0, let's say, then this will just become a transformation corresponding to doing nothing, which is just identity, which is 1. So we'll have T of theta being f of theta comma 0. Similarly, if we set theta to be 0, we will have f of theta bar to be some f of 0 and theta bar, and we can just rename theta bar to theta because it's just a label. So we can, in particular, we can say that f of theta 0 and f of theta 0 and theta bar is the same as this argument. These arguments should be the same. So this is just theta or theta A. This puts some restrictions on the form of theta, form of f, because now we can say that f as a function of theta and theta bar can have these sort of terms, theta bar. If there is an A index here, we will have an A index here, plus some combination of theta and theta bar. Let's call it A, B, and let's call this guy, I don't know, no, wait, let's call it BC, right? Yeah, we can call it BC. And we'll have some constants here. And this is summed over, of course. B and C's are summed over. We will not have theta square terms, theta square or theta bar square terms, or terms in general. We will not have terms which are quadratic or higher order in theta, because that would violate this condition. If you were to, let's say, put theta bar equals 0 and there were theta square terms here, then all of these would go to 0, but theta square terms would survive. But this condition tells us that if you put theta bar to be 0, you should have theta, which you should just have one theta, linear theta, not a theta bar term or neither a theta square term. And similarly, same argument for theta bar. So that this is why we have another terms would have, let's say, theta bar, theta, and I don't know, theta bar, one more theta bar I think can work, because again, if you put theta equals 0, these will go to 0. If you put theta bar to be 0, again everything, this term will go to 0. So there cannot be individual terms of this type for n greater than or equal to 2, or we cannot have theta to the power n type of terms as well. Okay, so we can have higher order terms, that is fine. So this condition puts restriction on the form of this function, which might be here. And secondly, we can assume that we can expand this t of theta, the unitary matrix that we have here, we can expand this unitary matrix around the identity as 1 plus some function, some term which is linear in theta, which is we have some matrices Ta here. These are Hermitian matrices in term because U has to be unitary, so that puts restrictions on what Ta can be. Tas are just Hermitian matrices. There can be another term which is quadratic in theta, which could be theta t. There can be another TBC, some other matrix TBC. There can be some constants here, and so on. There can be higher order terms as well. This represents the expansion of the unitary matrix in the neighborhood of identity. So now we just have to use this condition, the defining condition, that U of t of theta bar and followed by U of t of theta is just U of t of some function of theta and theta bar, where we have put restrictions on the form of f like this. So the full thing would look something like this. So U of t of theta bar would be 1 plus I theta bar t. I'm just not putting the indices for now. It would be theta t, then sorry, this is theta bar. Okay, the other would be this second term would be 1 plus I theta t plus half of theta t bc. So it's a second term tbc. Here we will also write tbc. I think I should put this there to keep track of things. Okay, and this is just U of f of theta bar, which is just this would be, since the form is of this type, we'll just have 1 plus I times, now the theta I should have some theta term times t. That's the linear term, but the theta is of this form, so I'll have theta b plus theta bar b, sorry, a plus some a b c theta bar b theta c, and then ta, and then my second order term, which again I'll have two theta terms followed by t b c. So here I will have a b term, theta b term, sorry, theta, which will have this theta bar, no, sorry, this sort of term I'll have. Okay, so for that I will have theta b plus theta bar b plus again fabc and so on. Again here I will have theta c plus theta bar c plus again the mixed terms. We will not need those higher order terms. Now we can just start expanding this. I'll just expand it, and alright, so I've expanded a lot of terms. We can start cancelling out the terms that we are seeing that are the same on the both sides. For instance, this is the same. I can see this one also goes away. I theta bar a theta t a also goes away. Other than that, let me see, half of theta bar b theta bar c tbc also goes away. And what else? I times fabc does not go away, and this thing is there, this thing is there, this thing is there. Okay, okay, because I have written this term out here and these two guys here, and I have not included this. This is theta cubed term, and this one is also theta cubed, so I have not considered those. The first order, the linear ones in theta, are cancelled out. The second order ones are written here. For instance, this is written here. The fabc term goes here, and these two terms I have combined because the b and c are summed over, so I can relabel b and c as c and b, and here as well c and b. And this guy is symmetric, tbc is TCB. This is a symmetric matrix, as you can see from the definition itself. This second order matrix TBC is symmetric because it's roughly the second derivative of u with respect to theta. This is of this form: d2u over d theta a d theta b. And since the order here doesn't matter, this is why TBC will be symmetric. So I can add these two, half and half becomes 1, so I have written this here. Rearranging, since this theta b and theta c can be removed from everywhere, again I can call this theta c, you can call it theta b. Yeah, this is fine. So this can become I'll single this one out. TBC can be written as minus TBTC minus IFABC, and we have TA. And again, since we can just shuffle B and C, so TCB would be minus TCTB. I'm just rearranging the B and C, as in replacing their order. CB, TA, and since these two are equal because they are symmetric, the right hand sides would also be equal. That would mean minus TBC, and this whole thing is same as this. Let me remove this. Yeah, these are same, and of course this guy can go there. We will have TCTB, and that guy can come here. We will have IFABCTA, this one, and this will just become, again we can also this will just become TBTC, so the commutator of TC and TB, and there we will have I times FABC minus FACB times TA, and we can flip the commutator here, TBTC, since T and T is our Hermitian matrices, and there we will have A times the minus of this thing, which would be CB minus F of ABC TA, and let me just call this CABC. Let me define it as this constant. So we will have the famous commutator relation IC, sorry, it was B and C, right? Yeah, BC and ATA. This is the famous commutation relation that defines the Lie algebra of the system, or the Lie algebra of the group. So CAB is called the structure constant. Wow, what a highlighter, nice. Okay, anyway, this is called the structure constant, and the reason is that this structure constant is coming from these f's, which are indeed coming from the structure of this f function right here, which is a function of theta and theta bar. Now suppose if this as a special case, we can consider if the function was just like this, there was no structure constant, CABs were 0, then we would have the commutators, TBTC would be 0, and therefore all these terms, TBTC and all the further terms, all these would become 0. Yeah. Then what we can wait, no, sorry, I said something wrong, I think. Yeah, what we can say, if these are 0, the other or the higher order term in f are 0, then we can say that this condition right here becomes, so right now I'm just talking about the special case where the structure constants f's are 0, or to say c's are 0, then f of theta and theta bar would become theta plus theta bar. So this is just saying that the way these transformations compose is that the angles, or not the angles, the parameters or the vectors, because they are carrying this a index, they just sum up. In particular, if you have, let's say, if you are writing this theta as n times theta by n, so what you can do is just write it like this: t of theta times t of theta times t of theta n times. And according to this rule, this would just become t of theta by n. Sorry, t of theta n theta, yeah. Or you can say that u of t of theta would become, sorry, there should have been a u here, I think. Okay, no, it doesn't matter. So u of t of theta, because now you can just take this n and divide it here by everyone like this. That t of theta by n times t of theta by n times t of theta by n times would just give you t of theta. So that would be u of t of theta by n times. So this u is multiplied by itself n times, and if you take the limit in which n goes to infinity, so you can expand this u, since u was like u 1 plus I theta t plus some half theta squared tbc and so on. Since we have each of these thetas, the argument is of form theta by n, so the higher order terms would be of form theta square by n square, theta square by n cube, and so on. And since n is very large, so these all these terms can be dropped and only linear terms suffice. So we can write this guy as limit n tends to infinity, and we can write it as 1 plus I by, so we have theta a theta by n, so we'll have this, and is whole to the power n, which is coming directly from there. And this is just the definition of exponential of I ta theta I. So this is I did it for the abelian case. Abelian meaning the order doesn't matter here of the way you are multiplying group elements, because this is just the sum. So you can do theta bar, theta t of theta and t of theta bar, that would be t of theta plus theta bar, that would just be t of theta bar plus theta, and that is the same as t of theta bar times t of theta. So these are equal. The order of composition does not matter. That is the abelian group. But this is not in general true. When there is a structure available, the commutator is given by the structure constants, and the idea is just like how we found that TBC. Look at this equation right here for a moment. Okay, just as we found that the second order matrices, which so in the expansion of T, we have these first order matrices TA, we have these TBCs, which are the second order matrices corresponding to the term which has theta squared. Similarly, we would have some T ABC something on the third order, and so on. So these second order matrices are evaluated from the first order ones like this, and the structure constant. Similarly, it can be shown that the higher order ones can also be written in terms of these second order ones and so on, and which can in turn be written as the first order ones. So what I want to say is all the orders are fixed once we know the structure constants, or we know these generators these first order generators. So these are enough to expand the whole unitary matrix around identity at least. Okay, so yeah, that was it. I think next time I can cover the Lorentz transformation thing.